All right, well, we're looking at section 5.9, volume of a solid by plane slicing. Okay, so what we're going to be doing is taking our little, whatever the shape happens to be, and slicing it up into little pieces. Okay, we're going to find volumes of revolution on this video, and then volumes of cross sections on the next one. Just like the rest of this week, we're starting with a U substitution review problem. On this one right here, remember that you cannot set your numerator equal to your u, because then when you take your one more time, when you take your derivative, it's going to end up being a dx and something funny, and it's not going to take care of your denominator. So what you want to do on these, set the denominator equal to your 2x plus 3 equal to your u, and then your du would be 2 dx. Well, I don't have a 2, so, I mean, that's going to have to move over. 1/2 du equals dx, but then that still doesn't take care of any of the things on the top, all these x's and stuff here. So what I want to do then is solve my u equation. Let me take it down here, and that will give me u minus 3 over 2 equals x. And then that I can plug in. All right, so I'm going to have an integral. X squared, x is u minus 3 over 2, so u minus 3 over 2 squared minus 2 times u minus 3 over 2 plus 5 all over your 2x plus 3 is the u, and then your dx is going to have a 1/2 du. Okay, now if you notice again, I do not have those boundaries. I have to figure those out. They're not going to stay -1 and 0 once I do u substitution. So I'm going to take my 0 and I'm going to plug it in right there. That's going to give me a 3. I'm going to take my -1 and plug it in. Same thing. And so I'll get a -2 plus 3, so that's going to be a 1. And those are going to be the boundaries for my integration. Okay, so let's kind of simplify things a bit here. I have 1/2 integral from 1 to 3 of, I'm going to FOIL this out, u squared minus 6u plus 9. It's over 4, but it's also over the u, so over 4u. On the next one, when I move it over, that's minus. Okay, my 2's can cancel out. And so that gives me minus a u minus 3 all over that u that's down in the denominator, plus 5 over u du. Okay, so 1/2 integral from 1 to 3, and then everything we're going to split into individual fractions. So u squared over 4u is going to give me u over 4, minus 6u over 4u, that just gives me minus 3/2, plus 9 over 4u. On the next one, don't forget to run the negative all the way through as you're doing this, but u over u, that's going to be minus 1, and then plus 3 over u, plus 5 over u, du. Okay. All right, so going through, trying to see here what might be a nice thing to integrate. I have 3 terms right here that have u's in the denominator. I'm going to be sure that I get a common denominator with those right there, since they all have the u in the bottom. So I have, again, 1/2 integral. Be sure you're watching your notation on this, keeping the 1/2 going, keeping the equal sign going down, that type of thing. So I have u over 4. Your negative 3 halves and negative 1 is negative 5 halves. My 9 over 4, and then I'm going to multiply each one of these times 4 in order to get that common denominator. Times 4 times 4. And so 9 and 12 is 21. 21 and 20 is going to be plus 41 over 4u du. Okay, well, we're finally down to the point where we can integrate. So that's going to be 1/2 times this whole thing in brackets. Integrate this, I'll get u squared over 2 times the 4, so u squared over 8. Minus 5 halves u. And then plus 41 over 4 natural log absolute value of u. Okay, and then all of this is going to be going from 1 to 3. Okay, I think from there y'all can handle it. If not, let me know and we'll answer questions tomorrow. Plug your 3 in all the way through, plug your 1 in all the way through. Again, let me know if you have questions, but I don't want to take up all your time just working this problem. So, here we go. Okay, disk method. Around the x-axis, this is really important that we recognize on the x-axis, y-axis would change things. This is going to be a region, and I should have said in quadrant 1, but I didn't quite get that in there. So you want to be sure you know that it's in quadrant 1, it's enclosed by y equals x squared, the line y equals 0, the line x equals 2, and it's rotated about the x-axis to form a solid. We want to write an integral for the volume and evaluate it. This is a whole new thing, all right? So let's take a nice little picture here and see what happens on this. If I'm looking at y equals x squared in the first quadrant, and that's going to be my parabola that comes up like this. The line y equals 0 is your x-axis, and the line x equals 2. Okay, so you're looking at that shape right there. Okay. Now, you know from the last couple of days that all you would do to integrate and find this area is to integrate from 0 to 2 of your x squared dx, not a big deal. But this is different. This is taking this area and it's rotating it around the x-axis to where you have another, you have a whole solid that's going to come down here. And use something similar to a horn when it rotates all the way around. Okay? That's a whole different thing. What you're doing on this is coming down, excuse me, and finding little pieces like that and rotating these little pieces, these little rectangles. And you'll see this in our project that we're doing. We're just going to take these pieces like this and rotate them around. Now when I rotate that little piece around like that, that's going to end up making a cylinder. The formula for the volume of a cylinder is pi times radius squared times height. Okay? And that's what we're going to do on this. That's the way that we're going to integrate this. We're going to have the volume equals pi, and then because our radius changes, our radius right here is going to be different than our radius right here, then right here, then right here, because our radius keeps changing. That's where we're going to put in our function. The length of that radius is x squared. Whatever x value I choose, that's what gives me my radius there. So pi x squared is the radius, and radius is supposed to be squared, so there's another square there. And then your height over here would be the width of that piece. Well, remember, your width of your piece is always going to be the dx. Okay, it would be the delta x if we were doing summation notation, because we're adding all these pieces up. It's going to be dx whenever we're rewriting this as an integral going from 0 to 2. Okay, because I'm still looking at that piece as if it's going from 0 to 2. All right, so then that means that writing this a little bit neater, integral from 0 to 2 of x to the 4th dx. So you have pi bracket x to the 4th goes x to the 5th over 5, going from 0 to 2. And when you plug your 2 in, 2 to the 5th is 32. So you have 32 pi over 5. The 0 plugged in would just give you 0, so there's your answer. And that's all that there is to it. It's not a hard thing at all. It does sometimes get a little bit confusing. All right, let's look at the next one. It's a little bit different. Okay. This time it says the disk method, but I am going around the y-axis. That changes everything. If you go back and look, when I went around the x-axis, then my whole equation over here was in terms of x. Okay? Well, then logically, when I start going around the y-axis, my whole equation has to be in terms of y. Everything has to be there. Okay? So I'm still looking, same thing. A region enclosed by y equals x squared. The line x equals 0 this time, so that's going to be my y-axis, and the line y equals 2. So I still have my nice little parabola coming out here, y equals x squared. But it's not dropping down like it did before. At this point, what it's doing, because it's going to the line x equals 0, it's coming back here. Okay, like this. And here's my line y equals 2 right there. Okay. When I rotate that around the y-axis, then this comes like this, and I have this type of shape. So something like a headlight type thing, or a half a watermelon, whatever you want to say, but there's our shape up like that. Okay, that's the solid that I'm trying to find the volume of. Now what that means on this one is that my pieces that I am finding look like this. I am slicing this thing horizontally. Okay, that right there is going to be my radius. Okay, instead of the up and down from the x-axis. Now then, because that is going to change based on how high I count up, that means my equation, instead of being written y equals x squared, now has to be changed to x equals square root of y. Now normally we would do the plus or minus on it, but I am only looking at this right-hand piece right here, so that's the positive value of that. And then that's going to be rotated around. Okay? So, same basic concept as you had before, volume equals pi, and then you want your radius squared. Well, your radius this time happens to be square root of y times your height, which is now then this width right there on that piece, and so that width is a delta y or a dy on this one. Okay. All right. So then you've got, and you are going. Sorry, I should put this in there, from 0 to 2. So you've got pi integral from 0 to 2 of y dy. So that is going to be pi times pi squared over 2, going from 0 to 2. Plug your 2 in. 2 squared is 4, over 2 is 2. So you get 2 pi, and your 0 is not going to have any impact. Okay. Questions or problems? Hopefully we're good. If you do have questions, write them down. Okay, next one. Washer method. Those others were disk methods because we were making a disk. A washer, if you remember, is something like this that has a hole in the middle. Okay? So this time I'm going to be going around the x-axis. Everything is back in terms of x again, but there's going to be a hole in the middle of my solid. So I need to find the volume of the entire thing and then subtract out the volume of the piece in the middle that is no longer there. I've still chosen to use y equals x squared. Okay. All right. So it's the region enclosed by y equals x squared, the line x equals 0, and the line y equals 2. So almost everything here still sounds like the piece that we just did. Sorry, let me see if I can get it like this so you can see better. That looks like that, except this time it's going around the x-axis. So that means what happens is that this is going to have to come down like this, and this is going to come across like this, and out like that. Okay, so what you have, if you've ever been to one of those places where you put a coin in the edge, you look at it, and on the outside it looks solid like this, but you put a coin on the edge and it rolls around on the inside, and there's this little funnel type shape on the inside of that thing, and that coin rolls around and around and around and around. This is that shape. The outside of this is completely solid. The inside of it is going to change. And I'll show you a little bit better picture whenever we're doing these in class, so you can see it a little bit better, but hopefully that makes sense. You need a solid thing on the outside, and then on the inside you've got this funnel shape that's been dug out of the middle of it. Okay? When we get to these, we're probably not going to do quite as much of our solving. We're going to try to get going on these pretty quickly. Okay? So I need my integral. Pi. Oh, I should put volume. Sorry, volume equals pi times, radius squared. Well, that's a little confusing because normally my radius, will go all the way out like this, but I've got this piece cut out of it. That part is not there on this. Okay? Well, what you've got to do is think of this. How far is it from the axis of rotation to that highest point? And it said it was going around the line y equals 2, so it's 2. My radius there is 2 squared. Okay? Then I have to subtract out that piece in the middle. Well, the piece in the middle, see, this stayed 2 the entire time because that's solid. The piece in the middle, though, keeps changing. All right? It's that piece right there, but then a little bit further up, it's this piece right here, and a little bit further up, it's going to be this piece right here. And so that piece keeps changing. Well, that was our x squared, wasn't it? Alright, so you want your outside radius minus the inside radius. And that, I'm going to come back and put your numbers in just a minute. Let me drop down here for a minute. Your volume on the washer method is pi times the integral from a to b. The outside radius, we'll do it capitalized minus that inside radius. Okay, that's what we're looking for. Okay, well, how do I find my bounds on this one? My A and my B that were down here, I need to know what those are. Okay, well, I know I'm starting at 0, so that's not a big deal. I can put my 0 in there. But it says my y value, again, going back to this right here, it says y is 2. That's where I'm stopping. Well, I need to know where that line, the y equals 2 right there, intersects the curve of x squared. So when I set, I'm going to just come over here to the side and set 2 equal to x squared, and x is going to equal the square root of 2. And so that means that this value right here is the square root of 2, that's how far that came, and that would give me that all the way up there. So this is going to be integrated from 0 to the square root of 2. Okay, so you got pi integral from 0 to the square root of 2 of 4 minus x to the 4th dx. And then you can integrate and plug things in and solve. Okay. All right. Let's do one more, and then I'm going to let you go because it's already getting pretty lengthy. We'll work the next couple of examples in class. You can tell that this is a pretty detailed set of material. All right, next one. We've still got our y equals x squared. Comes up like that. The line y equals 0, and the line x equals 2. So that means I'm coming down right here. Okay? And the line y equals 0. I'm looking at this shape right here, but then I am rotating it around the y-axis. Okay? So that means I am rotating it around like this. So what I have is, from the outside, it looks like a solid cylinder, okay? It's going to look just like this from the outside, but on the inside, I have this little parabola cut out of it. So if you think about a salad bowl, it looks perfect like a cylinder from the outside, but if you look on the inside, it scoops out into this nice little curved space for you to put the salad in, something like that. Okay? So that's going to be volume equals pi times my integral. Now then, I'm going to have to work a minute on those values to figure out my a and my b, but we'll get there. On this one, because I'm going around the y-axis, this is my little slice right here. So my outer radius, this outer radius is going to stay the same the whole time. That's going to be 2, because it said x equals 2. So I've got 2 squared. That's my outer radius. Minus, on this one, I'm subtracting out this inner piece right here. I should have done blue, sorry y'all. So that you can see it a little better. I'm subtracting this out. And that piece changes every time, doesn't it? Okay, that outside radius is still going to go out there and be 2, but that inside radius is going to change. That inside radius, again, has to be in terms of y. So if y equals x squared, then my x is going to be the square root of y. So 2 squared minus the square root of y squared. That is my outer radius minus the inner radius dy. Okay? Finding your boundaries on this. The bottom one's easy. Bottom one's 0. But the top, I've got to figure out how far up this thing goes. Okay? Well, if it told me that x equals 2 was this line right here, then when I plug that in and I have y equals 2 squared, my upper boundary then would have to be 4. Okay. So then simplifying this out, I've got pi times the integral from 0 to 4 of 4 minus y dy. And if I go through and integrate that and find my area, or plug in my values, then I will find my volume. All right? Okay. Tomorrow in class, be ready. We'll try to figure out which method we want to use on this one, and then look at things rotated around some axis other than x or y. And it makes for a challenge. All right? And, oh, maybe I did 2 of this. All right. Here's your quick reminders. You might want to pause it and copy these down. Okay, that's when it's a disk. If you're going around the x-axis, you want everything in terms of x. If you're going around the y-axis, you want everything in terms of y. Okay, and then here is your washer method. Okay, outer radius minus the inner radius. Okay, if the axis of rotation is not a primary axis, you do not know how to do it yet. So we will do that then in class. But hopefully that gets you going on this. and we'll talk to you later.